As advertised, today we are going to be discussing quantum physics as it relates to our document. So, in this first major section of part one, we talk about a physical world. We discuss what we can take from the physical sciences today. We basically commit to this type of understanding of the world. It suggests that the universe is composed of matter and energy governed by consistent observable laws. This type of discussion can bring in the idea that perhaps, despite the fact that this exists, despite the fact that this is a basic tenet or axiom that we operate under, quantum physics has some effect on consciousness and our freedom, our understanding of the world, that takes us outside of this realm of consistent observable laws. Of course, following the same laws of quantum physics, but now operating in a indeterministic, non-deterministic. Yeah. So basically, I just wanted to look over this chat that I had with Gemini, going over these ideas, considering how quantum physics actually connects with the idea of consciousness, etc. Because I've heard of theories about this. I just wanted to figure this out once and for all. And granted, I'm not qualified to speak on or teach quantum physics. That said, this conversation seemed to be pretty clear cut. I guess if there's any feedback on where it's not right or where I go wrong with this conversation, then let me know. But I think I'm just going to read through it, and then we could discuss how it connects with our document. All right, so I pretty much started this off by asking, what is the branch of science/philosophy that considers whether quantum physics has a relevant/significant effect on our consciousness/freedom? The area of inquiry that explores the connection between quantum physics and concepts like consciousness and free will is a highly interdisciplinary and speculative field, primarily situated at the intersection of the philosophy of physics and the philosophy of mind. It doesn't have a singular, universally agreed upon name, but it is often referred to as the study of quantum consciousness or the quantum mind. This field investigates the possibility that the strange and counterintuitive phenomena of quantum mechanics, such as indeterminism, superposition, and the observer effect, might play a significant role in explaining the nature of consciousness and the existence of free will, aspects of human experience that classical physics struggles to account for. So key concepts and theories. At the heart of this exploration are several key quantum concepts that are hypothesized to have relevance to consciousness and free will. Indeterminism. Classical physics is deterministic, meaning that if you know the initial state of a system, you can, in principle, predict its entire future. Quantum mechanics, however, is inherently probabilistic. This indeterminism is seen by some as a potential opening for free will, suggesting that our choices might not be predetermined. There's this concept of superposition. This principle states that a quantum system can exist in multiple states at once until it is measured. Some theories propose that the brain might utilize quantum superposition to explore multiple possibilities simultaneously, which could be a basis for decision-making and creativity. So I guess just to give a little bit more on superposition, you could scale this up by first thinking about an electron being in one or two different states, spin up or spin down, and there's a superposition that is often represented, or I think it is represented by some equation. It's like an equation that represents both of these positions that the electron could be in, and so you could actually scale that up to take into account multiple electrons. So there's, you could say the superposition of these 5 electrons, and your equation kind of represents all the different possibilities that these electrons could be in. And it also represents the probability that, like the distribution of probability that each of those states, could possibly be in. And then you could scale this up to the entire universe. So you could say there's a superposition of the entire universe that could be represented by some equation that takes into account every single electron and has the probability of every single electron baked in. So, yeah. Some theories propose that the brain might utilize quantum superposition to explore multiple possibilities simultaneously, which could be a basis for decision-making and creativity. All right, then there's this idea of observer effect. In quantum mechanics, the act of observing a system can fundamentally change its state. This has led to speculation about the role of consciousness as an observer that collapses the quantum wave function, suggesting a more active role for consciousness in the physical world. All right, so these are kind of key concepts and theories that allow you to start thinking about consciousness in relation to quantum physics. Dominant hypotheses. Several specific theories have been proposed within this field. The von Neumann-Wigner interpretation, this interpretation of quantum mechanics, championed by physicists Eugene Wigner and John von Neumann, suggests that consciousness is what causes the collapse of the wave function. And then there's the orchestrated objective reduction, OR theory, developed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. This is one of the most detailed and controversial theories. It posits that consciousness arises from quantum computations occurring in microtubules within the brain's neurons. All right, so ongoing in debate and skepticism. It's important to note that the field of quantum consciousness is highly speculative and is met with significant skepticism from many physicists and neuroscientists. Critics argue that the brain is a warm, wet, and noisy environment where delicate quantum effects would be destroyed almost instantly through a process called quantum decoherence. They contend that classical neuroscience and computation are sufficient to explain brain function and consciousness. Despite the controversy, the study of the potential links between quantum mechanics and consciousness continues to be an active area of philosophical and scientific debate, pushing the boundaries of our understanding of both the physical world and our own minds. So, coming into this conversation, I wanted to get a sense of how prominent these ideas are and what their logical presuppositions are, etc. Like, what does this space look like? All right, so I ask, okay, I want to consider the validity of this connection. First, regarding indeterminism, how much of the quantum physics field holds that the most plausible takeaway from quantum physics is indeterminism? Is the many worlds interpretation necessary in order to consider how quantum physics can be deterministic? As discussed by this book that I read, Sean Carroll, Something Deeply Hidden. In our document, we take this stand about determinism. Determinism lies at the heart of our physical understanding of the universe. It holds that every physical event, from the movement of planets to the firing of neurons in our brains, is the inevitable result of preceding causes. All right. As a physical structure, the brain must operate within this deterministic framework, following the same predictable laws that govern the rest of the universe. This idea that quantum physics introduces indeterminism is potentially assaulting the way that we go in our document. So let's continue. I'm just going to skip over any glazing by Gemini. Let's break down the validity of that connection. In short, while indeterminism is a very popular and widely taught takeaway from quantum physics, it is not universally accepted by physicists. And crucially, the many worlds interpretation is not the only way to have a deterministic quantum theory. So the status of indeterminism in quantum physics. The idea that quantum physics implies true fundamental randomness in the universe stems primarily from the Copenhagen interpretation, which is the historical and most commonly taught framework. In this view, a quantum system exists in a superposition of all possible states. For example, an electron is in multiple locations at once. When a measurement is made, this cloud of probabilities undergoes a wave function collapse, and the particle randomly lands in one definite state. This collapse is seen as an inherently indeterministic process. You can predict the odds, but you can never know the specific outcome in advance. However, how much of the field actually holds this view? It's complicated, and there's no single consensus. Various polls of physicists physicists and experts in quantum foundations have shown that while the Copenhagen interpretation is popular, a very significant portion of the community finds it unsatisfactory and is open to or prefers other interpretations, including deterministic ones. So the claim that quantum physics proves the universe is indeterministic is a strong one that many physicists would dispute. It's more accurate to say that it's a plausible and widely held interpretation, but not a settled fact. All right, deterministic alternatives. It's not just the many worlds interpretation. This brings us to your second question. Sean Carroll is a leading advocate for the many worlds interpretation, which is indeed a deterministic theory, but it is not the only one. The other major deterministic alternative is Bohmian Mechanics. Here's how they differ in achieving determinism. All right, the many worlds interpretation, as Carroll describes, achieves determinism by getting rid of the wave function collapse. It posits that the Schrödinger equation, the core mathematical formula of quantum mechanics, which describes how a system evolves over time, is all there is. This equation is perfectly deterministic. So what happens when a measurement occurs? Instead of a random collapse into one reality, the universe branches. Every possible outcome of a measurement happens, each in its own separate parallel world. You, as the observer, split along with the system, with one version of you seeing one outcome and another version seeing a different outcome. There is no randomness, just a branching of realities, all of which are equally real. All right. And like, I guess that's a prospective way to look at it. You could also just consider that there's just multiple versions of you that, you know, like if time wasn't this sequential, if time doesn't just have a start and end and it's just always going forward, you can think about, you know, the stuff that happens in the future as already being there, especially in a deterministic sense. So all these splits have already happened essentially, but, you know, as we're going through them in time, as we're experiencing this, it seems that, you know, we can interpret it as a split. Bohmian mechanics, or pilot wave theory. This is the other leading deterministic theory, first conceived by Louis de Broglie and later developed by David Bohm. Bohmian mechanics takes a very different approach. It claims that particles always have definite, precise positions even when we aren't measuring them. In addition to the particle, there's always a pilot wave, which is the same as the wave function in standard quantum mechanics. This wave is also real, and it deterministically guides the particle's motion like a current guiding a twig in a river. The apparent randomness we see in experiments is not fundamental. It's simply a result of our ignorance about the particle's precise initial position. If we knew the exact starting position of the particle and the state of its pilot wave, we could predict its future trajectory with certainty. In this view, there is only one world, and there is no random collapse. Everything unfolds deterministically. Therefore, to consider quantum physics as deterministic, you are not forced to accept the seemingly extravagant idea of infinite parallel universes. The Bohmian perspective offers a deterministic model within a single unified reality. All right, so then I say, okay, so perhaps the first distinction that we should make is that of perspective. The nature of empirical science is subjective in that it requires a measurement and a subject to read/interpret that measurement. Intuitively, it seems like the wave function collapses as we measure with our eyes. From our point of view, we are only dealing with probability, described by representations of superposition. With the many worlds interpretation, we acknowledge less authority towards the subjective observer. In this case, measurement does collapse the superposition, but does not. I meant to say does not collapse the superposition, but rather, for lack of better words, tells you which world represented within the superposition of the entire universe you're in. So that's like going back to what I just said about how you can think about these splits having already occurred. Whenever you see reality, and you know, you could say this is the measurement, you're seeing the reality that you are in, basically. Like, you're coming to discover which of the worlds, of the many worlds, you reside in. And you don't know, essentially, like why that's the case. At every moment of at every split, you know, it's deterministic what the outcomes of that split are, and therefore within this, you know, many worlds situation. Everything is kind of transpired deterministically. And that's not ultimately satisfactory when we think about things, because we like to think about a single world, and that's kind of how our brain operates. However, that's what that interpretation gives us. With Bohmian mechanics, we acknowledge the inherent ignorance of the subjective observer. In this case, measurement is necessary to see the world as it truly is in a physical material sense. Finally, what would you speculate is the rough distribution of how popular each of these perspectives are? Has there been clear science that has, not disproven either, but has rendered one of these more precise and plausible speculatively than the others? You provided a summary of the philosophical distinctions between these interpretations. You're right that the core difference lies in the role and nature of the observer and the act of measurement. So for the Copenhagen indeterminism, measurement is a special physically real process that introduces randomness and collapses possibilities into a single actuality for the observer. The observer's measurement is central. For many worlds, measurement is simply a normal physical interaction that entangles the observer with the system, causing the universal wave function to branch. It tells you which branch you're on, but it doesn't cause a special collapse. The observer's subjective experiences of a single outcome, but this is an illusion of perspective. And then in the Bohmian mechanics, measurement is also a normal physical interaction, but its role is epistemic. It reveals the pre-existing definite state of the system that was previously unknown to the observer. It's an admission of the observer's necessary ignorance. Now let's address your questions about their popularity and plausibility. What is the rough distribution of popularity? This is a notoriously difficult question to answer precisely, as views change over time and depend heavily on who you ask. For example, theoretical physicists, experimentalists, philosophers of physics. However, various informal polls and surveys conducted at conferences over the years give us a rough idea. Here's a speculative but educated breakdown based on those surveys. Copenhagen-like interpretations, approximately 40 to 50%. This remains the most common default view, largely because it's what's taught in most textbooks. It's pragmatic, focused on predicting experimental results, and doesn't make grand metaphysical claims about unseen realities. Many physicists adopt a shut up and calculate attitude, which aligns with the practical focus of the Copenhagen interpretation. This category also includes modern variations like quantum Bayesianism. Many worlds interpretation, about approximately 20 to 25%. The popularity of many worlds has grown significantly in recent decades, especially among cosmologists and theoretical physicists working on quantum gravity. Its primary appeal is its mathematical elegance. It requires no new physics beyond the deterministic Schrödinger equation. It simply takes the existing math at face value. So then there's Bohmian mechanics. Bohmian mechanics has always been a minority view, though it has a dedicated and persistent following. It was historically dismissed for various reasons, but it has seen a revival as physicists have taken quantum foundations more seriously. Its appeal is that it restores a sense of realism and determinism that many find comforting. Okay, so I'm kind of picking up that a lot of this is based on people's intuitions about the world, like their own metaphysical intuitions about the way the world is. And so these are interpretations of very similar math. All right, information-based / other, 20 to 25% approximately. A large and growing camp of physicists believe the central issue is one of information. Interpretations like cubism, which I believe that was quantum Bayesianism, and relational quantum mechanics see the wave function not as a real physical object, but as a representation of an observer's knowledge or information about a system. This category lumps together many different emerging ideas. So while Copenhagen-style thinking still holds a plurality, there is no overwhelming consensus. Many worlds is a strong and growing contender, while Bohmian mechanics remains a significant but smaller alternative. Has science rendered one more plausible than others? This is the billion-dollar question. The answer is no, not directly. The immense difficulty is that all major interpretations are constructed to make the exact same experimental predictions. As long as that's the case, no experiment can definitively disprove one in favor of another. However, science has clarified the profound strangeness of the reality that any successful interpretation must explain. The key development here was Bell's theorem and the subsequent experiments that tested it. So what Bell's theorem did In the 1960s, physicist John Bell devised a mathematical theorem that showed any theory based on two common sense assumptions: locality, no spooky action at a distance, and realism, properties exist before they are measured, would make slightly different statistical predictions than quantum mechanics. The experimental verdict: experiments have been performed with increasing precision for decades, and they have resoundingly violated Bell's theorem and confirmed the predictions of quantum mechanics. This has profound implications for plausibility. It tells us that any valid interpretation of quantum mechanics must abandon at least one of those common sense assumptions. You cannot have a universe that is both locally causal and has definite pre-existing properties. So Bohmian Mechanics saves realism. Particles have real positions, but must sacrifice locality. It requires an instantaneous, spooky action at a distance where the pilot wave can influence particles across the universe instantly. Many physicists find this non-locality deeply unappealing and difficult to reconcile with relativity. The many worlds interpretation saves both realism and locality. There's no spooky action, but it comes at the metaphysical cost of accepting an unobservable, infinitely branching multiverse. Now, the thing that I actually, to bring up with the many worlds that I found incredibly compelling in Sean Carroll's Something Deeply Hidden, and this is also speculative, but the universe isn't infinitely large in its amount of electrons. I think the idea, or the speculative idea, is that there's a discrete number of electrons, and like going back, there's a discrete number of splits. You could think about, a split causing a new universe, and you could now think about, how incredibly large this number of universes would have to be. However, as long as it's discrete and not infinite, then now we're dealing with a situation where there are universes that simply don't exist, and there's many, many universes that are very similar to each other, depending on the superposition of the universe, the wave function that describes what position these electrons could be in. So, now when you get to the idea of moving your hand through a wall or something like that, you could say, even though there is an incredibly huge amount of universes, it is even more impossible that you can just float through a wall. The amount of things that would have to go your way is, it's more rare than the amount of universes we're in. So it's highly, highly unlikely, down to zero chance, that there's a universe where you float through that wall. So yeah, that's our way, that's a way you could think about the constraints of a many worlds type of situation. And I don't actually understand, how do we start thinking about superposition when we get to a incredibly large amount of worlds, but still not an infinite amount of worlds? How many of these worlds would look almost exactly the same as the one that you're operating in? So, similar enough that you would perceive it at least the same way. And then we can start considering, okay, what would be the most significant differences? And for the quantum consciousness person, they would want to look towards what's happening in the brain and consider, okay, how does this experience of consciousness relate to that, that side of the many worlds situation. The Copenhagen interpretation sacrifices realism. It claims that properties like position or spin are not real until measured. It's vague about the line between the quantum and classical worlds, and feels incomplete to many. So that was, by the way, that was one of the reasons why Sean Carroll was pushing for many worlds, and it was because it saved both of these at a more intuitive metaphysical cost. And I think I say something like that. So while no interpretation has been disproven, these tests have sharpened the choice. The question of which is more plausible now comes down to a philosophical and aesthetic choice of which weirdness you prefer. Do you sacrifice realism for a single but fundamentally random world? Copenhagen. Do you sacrifice locality for a single deterministic but non-local world? Bohmian. Or do you sacrifice singular reality for a local, deterministic, but branching multiverse? Many worlds. Currently, the scientific community remains deeply divided on which pill is easiest to swallow. All right, so then I say, okay, so this becomes an interesting dilemma. We are dealing with multiple interpretations about the behavior of matter, each following the same equations, and the axioms against which we are qualifying these interpretations are similarly conceptual and intuitive. So these ideas of locality and realism, like we're kind of basing this off of our understanding of what makes sense. So the idea of action at a distance doesn't make sense to us in line with what we know about the physical world and laws of physics, etc., except for through quantum physics. It's just not intuitive. Like gravity is pretty intuitive, even though we don't quite understand like what like gravity is at the end of the day. It's very empirical. Like thermodynamics seems pretty empirical, but something like spooky action at a distance, is rightly called spooky. So, however, the many worlds interpretation nevertheless abides by both locality and realism, yet challenges a third intuitive axiom. So we are in a position to consider which axioms we are most compelled by. So of those three axioms, like, are you more weirded out about spooky action, about realism, or about there being many worlds? This is where Sean Carroll jumps in with his argument in Something Deeply Hidden, pointing out the arbitrary concept of wave function collapse, why measurement has the effect that we perceive it having, and lastly, maintaining a sense of determinism and locality. Nevertheless, I still want this to be a conversation about the effects of quantum physics on consciousness and experience freedom. In my mind, it's rather intuitive and easy to argue that in a deterministic system, whether that is many worlds or Bohmian mechanics, given what we know about the correlation of brain activity and our conscious experience, our experience of consciousness and freedom don't have some supernatural effect on the physical universe. Rather, we can consider how physics has an effect on our experience. So, yeah, I'm getting to this point where we really want to hone in on the argument against this idea that physics has the effect on our experience, and rather that like consciousness somehow has an effect on the physical universe that is out of our view. Okay, now the tricky part of this is that it still feels like our experience has an effect on reality, and it would take some time to explain why this might be. And this is what we do in the document. Our experience is a manifestation of brain activity. That very brain activity affects the trajectory of our brain's development, resulting in how we experience the world in the future. Thus, subjectively, it would seem that by thinking certain things, that has an effect on the outside world. What's ultimately happening can be described by neurodynamics with or without quantum physics, which of course is at play in all quantum or all physical systems. Okay, now it seems more difficult to explain how a non-deterministic physical world could give us the same amount of certainty about the relationship between the physical world and our consciousness and experience freedom. Certainly, we must still acknowledge the empirical correlation between brain activity and experience, along with our understanding of neurodynamics and plasticity. However, there's now this hole which seems to welcome in theories about some type of supernatural freedom or soul that has some significant effect. I think we can conceptualize two ends of this issue: the input, the experience of freedom, and the output, its effect. The Copenhagen interpretation and its indeterminism seems to open the opportunity for considering that our experience of freedom is not merely a manifestation of underlying physical processes, akin to a non-physical soul, or that the effects of our experience freedom is not necessarily local, affecting broader implication and collapsing the universe's superposition. Before we consider the plausibility of either of these notions, I want to know if there are other angles at play that I'm overlooking. Let's now dive into the specific theories that have been proposed regarding consciousness and collapse. So it says, you have framed the dilemma with clarity. Your breakdown is precisely the line of reasoning that leads philosophers and physicists down this fascinating and contentious path. You're correct that in a deterministic framework, be it many worlds or Bohm's, the problem of free will becomes a compatibilist one. Our feeling of freedom is real, but it's an emergent property of a deterministic physical system, the brain. So that's the take that we do in this document. Your central point is the crucial one. The indeterminism of the Copenhagen interpretation appears to leave a hole in the otherwise closed system of physical causation. This is the opening where speculative theories about the role of consciousness take root. You conceptualize the two main possibilities stemming from this hole, one concerning the input, the nature of consciousness itself, and one concerning the output, the effect of consciousness on the physical world. This is a perfect segue into the specific theories that have been proposed because they generally focus on one or both of these points. Before diving into the theories, let's address your question, are there other angles at play that I'm overlooking? Yes, one crucial angle that you're touching upon is the famous hard problem of consciousness, which is something we actually touch on right here. The hard problem of consciousness. All right, the crucial angle you're touching upon is the famous hard problem of consciousness, a term coined by philosopher David Chalmers. The easy problems are about explaining the brain's functions, how it processes information, integrates sensory data, controls behavior, etc. Neurodynamics can, in principle, solve these. The hard problem is about explaining why we have subjective experience, qualia, at all. Why does the firing of C fibers feel like pain? Why does a 700 nanometer wavelength of light look like red? Classical deterministic physics offers no explanation for this. It can describe the machinery of the brain, but it has no language for subjective experience. This profound explanatory gap is the primary motivation for looking to quantum mechanics. The thinking is, if classical physics can't explain consciousness, and quantum mechanics is the next deeper layer of physics, perhaps the explanation lies there. So the hole left by indeterminism isn't just a place to insert free will, it's seen by some as a clue to solving the hard problem of consciousness itself. All right, so specific theories of consciousness and collapse. Let's dive into the major theories that try to connect consciousness to the collapse of the wave function, filling that hole you identified. So we got the von Neumann Wigler interpretation, consciousness causes collapse. This is the most straightforward and radical proposal, directly addressing your output angle. The theory, championed by brilliant mathematicians and physicists like John von Neumann and Eugene Wigner, this interpretation posits that the wave function collapse is not caused by an arbitrary measurement from a Geiger counter, but specifically by the act of observation by a conscious mind. The physical world remains in a superposition of all possibilities until a conscious agent perceives it, at which point that agent's consciousness forces a collapse into a single definite state. Implications. In this view, consciousness is a fundamental and non-physical entity that stands outside of the material world and acts upon it. It solves the measurement problem by defining what a measurement is. It's an interaction with a mind. This directly validates the intuitive feeling that our experience has a tangible effect on reality. Plausibility issues. This view has fallen out of favor for several reasons. It introduces a sharp mind-body dualism that most scientists reject. It also leads to paradoxes like Wigner's friend, where one observer's reality remains in superposition until another observer asks them what they saw, creating a confusing causal chain. It is also fundamentally untestable. All right, so the second one here, orchestrated objective reduction, OR. Consciousness is a physical collapse. This is the most detailed and famous theory developed by Sir Roger Penrose, a physicist, and Stuart Hameroff, an anesthesiologist. It's far more nuanced than the Wigner view. The theory, OR, is built on two main ideas. Objective reduction, this is Penrose. Penrose argued that that wave function collapse is a real physical process, but it's not random and not caused by consciousness. He proposed that the collapse happens automatically, it's objective, when a superposition reaches a certain critical threshold of space-time curvature. The larger the object, the faster it collapses. This is a new physical law he proposes. Orchestrated, this is Hameroff's part. Hameroff suggests where this process happens in the brain. Within microtubules, which are protein structures that form the cytoskeleton of neurons, he argues that quantum computations can be sustained within these microtubules, shielded from the noisy environment of the brain. When these quantum computations reach Penrose's objective threshold, they collapse. The twist on consciousness and freedom, according to Orch, each moment of objective reduction is a moment of conscious experience. Consciousness doesn't cause the collapse. Rather, the orchestrated sequence of collapses is consciousness. For free will, Penrose adds another radical idea. He suggests the outcome of the collapse is not random, as in the Copenhagen view, nor fully determined. Instead, he argues it is non-computable. It cannot be predicted by any algorithm. This non-computability, he speculates, is what allows for genuine understanding and freedom, distinct from both deterministic algorithms and simple randomness. Plausibility issues. The primary scientific objection is quantum decoherence. The brain is considered far too warm, wet, and noisy to sustain the delicate quantum states required for the theory to work. Most physicists believe any quantum coherence in microtubules would decohere almost instantly, long before it could be relevant to thought processes. Okay, so then I say, okay, let's walk through these. For the von Neumann-Wigner interpretation, I think it is rather profound to think about measurement as fundamentally happening through subjective conscious observation. Even if we posit that some measurement device gets the true, accurate reading, it is only once we look at that reading that we know determinately that description of the physical world. Perhaps there are ways scientists have proven otherwise. Please let me know if there are. Intuitively, this seems like something we could not possibly disprove. Now, a few considerations. First, it doesn't seem logically sufficient for conscious observation causing collapse to necessarily imply that consciousness stands outside of the material world and acts upon it, the input problem. One could also argue that consciousness stands inside the material world and yet acts upon it. Furthermore, how does this theory make sense of multiple people collapsing the wave function at the same time? So I must have just missed the whole friend thing. Do the people who I interact with physically abide by my collapse, their collapse? If we share a world, then who has the authority? This seems more like a philosophical, existential way to think about quantum physics. Given that everything we know is subjectively interpreted, this seems to only make conceptual sense of our own experience. Now, for the Orch, which is what we're looking up right now, this seems to rectify our first issue with the prior theory. Consciousness stands within the physical world, or at least our physical description of it. In my mind, this theory introduces yet another hard problem. Even if it provides a description of what causes consciousness, it doesn't provide a comprehensive description of why this results in a subjective experience. It seems that this non-computable description introduces significant ambiguity, given that there is a correlation between experience in the brain, relevantly in the sense that we can see empirical changes to the brain when we learn certain information or skills. Where does this idea of distinct, genuine understanding and freedom come into play? And then it seems that quantum decoherence throws the ultimate wrench in this idea. Finally, regardless of each of these interpretations, it still seems incoherent to me why these would actually affect some new supernatural output that isn't simply explained by neurodynamics / plasticity / learning, etc. In other words, even if consciousness had some quantum significance, how is it that our determinate thoughts, which are at least partly manifestations of empirical brain activity, have clear effects on the physical world that are conceptually and coherently connected to the determinate concepts of the thoughts themselves? All right, I'm going to say that again, because this is kind of crazy. Even if consciousness had some quantum significance, how is it that our determinate thoughts have clear effects on the physical world that are conceptually and coherently connected or similar to the determinate concepts of the thoughts themselves? So, for example, manifesting something in the world would involve some quantum mechanism happening in the brain that would somehow cause the exact conceptual outcome externally that I'm conceiving of. So even with action at a distance, what explains the exact conceptually related action at a distance? So if I were to conceptualize something or manifest something very specific to happen anywhere else, or, even, we can make this really intuitive when we talk about something like, remote consciousness. What's the idea that you can, get into a sensory deprivation tank and remote viewing. So remote manifesting is something that people can intuitively see as implausible. But then similarly, like how does your thoughts about something specifically happening in your brain affect those outcomes? Other than, I should hold on that one, because there are like situations where you can focus on certain things that do affect how your body reacts, but we could also make sense of those when we look at the brain activity. But yeah, so that's generally the question: how how would the quantum physics actually like connect with your thoughts happening, unless you just consider that the concepts themselves, what you're thinking about conceptually, that I will be doing this thing or that this thing will happen, is somehow the quantum physics like at play. Like the concept itself is the quantum physics manifesting. And I guess you could hold that, but we're now getting into a space that's where you are just operating on faith. Okay, you've just articulated the very critiques that keep these theories on the speculative fringes of science and philosophy. Your analysis is all right, and you're asking precisely the right questions. Let's walk through them, because you've hit the core of the issues. On the von Neumann-Wigner interpretation, based on your assessment, it is only once we look at that reading that we know determinately that the description of the physical world. Intuitively, this seems like something we could not possibly disprove. This is the philosophical strength and the scientific weakness of the VNW interpretation. It aligns perfectly with our own subjective solipsistic experience. You can never, in your own experience, prove that the world isn't in superposition until you looked. However, science operates on the Copernican principle, the assumption that we are not special observers in a special place. The VNW interpretation violates this principle in the most extreme way possible, placing a conscious observer in the most special position imaginable, as the creator of reality. While not disprovable from a first-person perspective, it's a non-starter for a scientific methodology that seeks objective, observer-independent laws. All right, so then the second thing I said, how does this theory make sense of multiple people collapsing the brain function at the same time? Who has the authority? And then this is just the Wigner's friend. Imagine a scientist, Wigner's friend, in a sealed laboratory who measures a quantum particle. From the friend's perspective, they see the result, and the wave function collapses to a definite state. But from Wigner's perspective, outside the lab, he doesn't know the result. Therefore, the entire lab, including the particle, the measuring device, and his conscious friend, remain in one giant superposition until Wigner opens the door and asks his friend for the result. This leads to a logical contradiction. Did the wave function collapse when the friend looked, or when Wigner looked? As you asked, who has the authority? The problem of nested observers with no clear rule for who gets to collapse reality is why the VNW interpretation is largely abandoned. It doesn't work in a world with multiple conscious beings. So on the Orch-OR interpretation, I said, this theory introduces yet another hard problem. It doesn't provide a comprehensive description of why this results in a subjective experience. This is a crucial philosophical point. Orch-OR proposes a neural correlate of consciousness. It makes the claim this specific physical process, orchestrated collapse in microtubules, is consciousness, but it doesn't and perhaps cannot explain why that physical process should feel like anything at all. It simply moves the hard problem from why does brain activity feel like something to why does an objective reduction feel like something. It trades one mystery for another. Then I ask, where does this idea of distinct, genuine understanding and freedom come into play? This was also regarding Penrose. This is a subtle but important part of Penrose's argument. He distinguishes between computation and understanding. A computer running a chess algorithm is performing a computation. A grandmaster looking at the board has a moment of insight or understanding of the position. Penrose argues that the brain's observable plasticity and learning are the computational parts. The genuine understanding, he speculates, is the non-computable result of the Orch-OR process. The problem, as you sense, is that this is a purely speculative leap. There is no evidence that understanding is a non-computable physical process or that such a process would grant freedom in a meaningful way. So this is once again a situation where we know there's a correlation between the computable and the non-computable result in this sense. But what's the line? When does the non-computable come into play? And when is this not just, like, why not just assume that these, like, our very thoughts are manifestations of brain activity? And yes, as you noted, the scientific consensus is that quantum decoherence makes the entire physical mechanism of Orch almost certainly unworkable in the warm, wet environment of the brain. So that just seems like this is the real thing that disproves that whole theory. The ultimate problem, the output or coherence question. This final point you raise is perhaps the most powerful objection to any theory linking quantum randomness / indeterminacy to consciousness or free will. How is it that our determinate thoughts have clear effects on the physical world that are conceptually and coherently connected to the determinate concepts of the thoughts themselves? You have put your finger on the amplification problem, sometimes called the translation problem. Let's break it down. A quantum event is a microscopic and, in these theories, fundamentally simple. It might decide if a single neuron fires or not. And then, of course, as we mentioned, that you can conceptualize like a larger abstract space that consists of multiple electrons. And then you can, consider, how these are all behaving, but they're not necessarily like operating in some super dependent sense, other than the fact that they're entangled. They might not be dependent in their behavior in a classical physical sense. So then a thought like I want to raise my arm is a massively complex, abstract, and conceptually coherent piece of information. An action like raising your arm is a macroscopic, coordinated, and goal-directed sequence involving millions of neurons and muscle fibers. So the gap between number 1 and number 3 is immense between the quantum event of a single electron affecting maybe whether a single neuron fires or not, and the macroscopic, coordinated, and goal-directed sequence. How does a random quantum nudge in a single neuron translate into the incredibly complex, orchestrated, and conceptually guided action of raising an arm precisely because you had the thought of raising it? And you would have to say that the thought of raising it is somehow, like through quantum physics, connected to the outcome. Like the thought itself is all those relevant quantum events occurring, and that's what's going from your volition, like your free will, to the actual event. Proponents might argue that the quantum event acts as a tiebreaker for a brain system that has already used classical computation to narrow its options down to a few choices. But this gives quantum mechanics a trivial role. It doesn't explain how the brain generated the complex, coherent options in the first place. A random nudge that makes you choose tea over coffee doesn't feel like a profound freedom. More importantly, it doesn't solve your core question about conceptual coherence. If you manifest a creative idea, the idea has intricate logical and aesthetic structure. What physical mechanism could ensure that a series of random quantum events in your brain's neurons produced a result that is not just a physical action, but a physical action that perfectly corresponds to a high-level abstract concept? There is currently no plausible answer to this question. This is the ultimate reason why most neuroscientists and physicists believe that consciousness and decision-making, while dependent on the quantum physics that underpins all matter, are fundamentally emergent, macroscopic, and classical phenomena of the brain's computational architecture. The feeling of freedom and the coherence of thought and action are products of that high-level system, not the direct output of low-level quantum events. So then I paste our document in, and I ask, how do the contents of part 1 of this document relevantly relate to our discussion? Would most neuroscientists and physicists agree with what part 1 says and implies about the relationship between quantum physics and the conscious experience of freedom? Because at the end of the day, this is what I'm really concerned about. All right, let's break down how part 1 of the StanRichson document relates to our discussion and how its perspective aligns with the mainstream scientific consensus. All right, so first, how does it relate to our discussion of quantum physics, consciousness, and freedom? Part 1 of the document is highly relevant to our conversation, but it approaches the problem from a fundamentally different and more mainstream scientific angle. Notably, it does not invoke quantum physics to explain consciousness or freedom. Instead, it builds a framework from the ground up using classical physics, evolutionary biology, and contemporary neuroscience. Here is how its argument relates to the core themes we've been discussing. It starts with the same problem. The document begins by establishing a view of the world as a physical world governed by deterministic laws. It immediately acknowledges that this raises a critical question about freedom and agency, and it identifies the hard problem of consciousness as a key limitation of a purely physicalist view. This is the exact same tension that led us to consider quantum mechanics as a potential explanation. But it chooses a different path, where quantum consciousness theories see a hole in physics to be filled by consciousness, for example, consciousness causing wave function collapse. The StanRichson document sees an explanatory gap to be filled by higher-level emergent processes. It argues that to understand consciousness and meaning, we must move beyond the purely physical and consider... So this is actually something that it says that I'm not super happy with, but... It says we must move beyond the purely physical and consider subjective experience and abstraction. This is where we get to make sense of the gap that the hard problem makes, like the gap between the actual physical science happening, the physical mechanisms, and the experience we have. So we kind of, we try to bridge that gap, but for the first part, for the actual physical stuff, we do try to ground that in the processes that would amount to the experiences that we're having of certain information, like the experience of knowing something. So it is epistemological in that sense. All right, its solution is grounded in neuroscience, not quantum mechanics. The document's core explanation for consciousness and our sense of freedom is built upon 3 pillars of modern cognitive science. The brain's evolved architecture. It grounds consciousness in the brain's layered, evolved structure where survival instincts, emotions, and higher reasoning are integrated. Embodied cognition. It argues that meaning is not just a mental event, but a physiological, affective, and action-oriented event. Our cognition is deeply integrated with our physical body and its interactions with the world. And predictive processing. This is the central mechanism of its framework. The brain actively constructs our reality by constantly making predictions about the world and updating them based on prediction error. Once again, just to mention, for predictive processing, this is like an interpretation of what's happening in the brain. So we can actually point to prediction error as the salient responses that our brain goes through when it occurs, something that breaks your expectation or doesn't abide by your expectation. We can empirically measure activity in the brain that strongly, looking at which parts of the brain are being activated at certain times, while certain behavior is occurring. This led to this predictive processing interpretation. It's not that our brain is computing expectations and we can see that expectation in as a physical thing that some repository is holding, and it's not like prediction error is some physical thing that is external in the world or something that happens in the brain. It's making sense of the brain's activity, and we get into that to show why that might be within part 1. So our experience of meaning, certainty, and even confusion are the felt subjective results of this predictive process working smoothly or encountering errors. Yeah, the nice thing about predictive processing as an interpretation, as a theory of what's happening in the brain, is that it connects a lot of dots. All right, its answer to free will is compatibilism. The document ultimately argues for a form of compatibilism. It concludes that freedom is not a magical ability to violate causality. Instead, freedom is an emergent capacity that exists within a deterministic system. It is the felt ability to engage in deliberate self-conscious reflection, examining our own understanding, and consciously realign our commitments and intentions over time, which in turn shape our future predisposition. So the conceptual understanding that we have that we're able to do things is still in line with causality, the determinism of our brain. We're just at this point where the manifestation of those physical processes is this thought that we can do something. And then, the thought that you actually go and do it. What interpretation of quantum physics do you subscribe to out of curiosity? I mean, the most compelling one the most compelling argument is the many worlds interpretation that I heard from Sean Carroll, because it, as mentioned in here, it makes sense of both locality and determinism. So that to me makes more sense than like a collapse. But once again, like as I'm trying to point out here, it almost doesn't matter practically, other than for the fact that there are physicists who, once they can grasp quantum computing, they could probably, that can amount to some pretty cool stuff, maybe. That's another instance where if we did figure out quantum computing, or I'm sorry, not quantum computing, but quantum physics in general, like what's actually going on, as we learn more about the universe, it gives people a lot more power. And there's going to be cool things that could come from that and very scary things that could come from that. My imagination is unfortunately a two-sided sword, double-edged sword. Doesn't the Copenhagen better fit Occam's razor? Okay, I don't quite understand Occam's razor. I've heard it, but is a philosophical and problem-solving principle, also known as the principle of parsimony, that states when multiple explanations for an observation are possible, the simpler one is usually preferable or likely to be correct. Well, this is the point that I was trying to make earlier on here. Let me find that. Okay, here. So Bell's theorem devised a mathematical theorem that showed any theory based on two common sense assumptions, locality, no spooky action at a distance, and realism, would make slightly different statistical predictions in quantum mechanics. The Copenhagen interpretation sacrifices realism. It claims that properties like position or spin are not real until measured. It's vague about the line between the quantum and classical worlds and feels incomplete to many. So the question is, what feels to you more compelling? Because the thing that the many worlds interpretation sacrifices is something that is intuitive. So the many worlds interpretation saves both realism and locality. There's no spooky action, but it comes at the metaphysical cost of accepting an unobservable branching multiverse. So the question is, what can you stomach? It's not a question of, like Occam's razor. I could argue that the simpler idea is, and let me just make sure I'm getting this again. The simpler one is usually preferable, or yeah, I guess. Okay, so Occam's razor is actually not making a case about what one is right. It's making the case of which one is usually preferable or more likely to be correct. Well, I guess that's, more likely to be correct. So, the question is which one is simpler in this case, and I would argue that simpler probably comes down to what you find most compelling. Which thing do you find more weird, actually? So it's, the question of which is more plausible, and I would say which is more simple, now comes down to a philosophical and aesthetic choice of which weirdness do you prefer? Do you sacrifice realism for a single but fundamentally random world, Copenhagen? Do you sacrifice locality for a single deterministic but non-local world, Bohmian? Or do you sacrifice singular reality for a local deterministic but branching multiverse? And in my mind, the multiverse thing still sits better with me, especially when I consider I don't know if you heard me talk about the discrete space of quantum events in the universe, but that would make it such that it's not like a infinite multiverse where it's like Rick and Morty, where you go into one and there's a chair that's talking to a pizza, or a pizza that's eating a fork. I forget what they were doing, but it would be more that there's a significant amount of universes in this many worlds theory that look exactly the same as ours. And it's very unlikely that the likelihood that there's a universe where, something crazy happens out of the, like I use the example of your hand going through a wall, because I think that's like some common quantum physics meme. The likelihood of that is so small that it's effectively zero, given the fact that there are a discrete amount of universes or many worlds. Like, even though that number is insanely huge, like we couldn't fathom how large that number is, the idea would be that still the superposition is such that the possibility or the probability that your hand can go through a wall is 0. So that whole thing sits well with me. That I don't know what that space looks like. I don't know what the distribution actually looks like, but I mean, it kind of, in my mind, it kind of fits with this idea of, the universe having multiple dimensions and us just not understanding what that might even mean. It just, I wouldn't be surprised if you could make sense of these things in that way, and that we obviously have this intuitive feeling because our experience is always within a single universe, or it's always within a single world that, or at least feels coherent. So, I mean, that to me makes sense of the fact that, our consciousness could be the deterministic effect of our brain functions. But I'm speculating at the end of the day. So where were we here? In short, the document provides a comprehensive alternative to the quantum consciousness theories. It argues that the mysteries of consciousness and freedom don't require a revolution in fundamental physics. They can be explained by the immense self-organizing complexity of the brain's predictive, embodied, and neurobiological processes. So number 2, would most neuroscientists and physicists agree with part 1? Yes, for the most part. The perspective offered in part 1 aligns very well with the mainstream consensus in both neuroscience and physics, which is precisely why it serves as such a strong counterpoint to this more speculative quantum theories. For neuroscientists and cognitive scientists, high agreement, the framework presented in the document is built on the dominant paradigms in contemporary cognitive science. The emphasis on the brain's evolutionary history, embodied cognition, and especially predictive processing reflects the current scientific zeitgeist. The document's to-do notes for part 1 even list many of the key thinkers in these fields, indicating its alignment with cutting-edge research. Now, granted, the to-do indicates that I haven't done it yet, so maybe we're not in alignment yet. The view on freedom. The compatibilist view of freedom is the overwhelming majority position among philosophers and scientists who study the topic. The idea that freedom is a complex psychological capacity for self-regulation and reflection rather than a metaphysical ability to break causal chains is widely accepted. Nuance. While the approach is mainstream, the specific synthesis and philosophical language used in the document is the author's own interpretation, which we self-consciously say in the document. Scientists would also agree with the document's repeated acknowledgement that the hard problem of consciousness remains unsolved. The document is offering a powerful framework for how to think about consciousness, not claiming to have solved it definitively. I mean, that's very similar to what I say all the time. We're offering a way to think about these things, not telling you how these things actually are. All right, so for physicists, they would strongly agree with the approach. Most physicists would strongly endorse the document's decision to not invoke quantum mechanics. The primary reason is quantum decoherence. Physicists are extremely skeptical that the delicate, large-scale quantum coherence needed for theories like Orch could survive for any meaningful amount of time in the warm, wet, and noisy environment of the brain. They would view the document's approach as appropriately respecting the different scales of scientific explanation, using neuroscience to explain the brain, not quantum physics. Implicit rejection of quantum consciousness. By grounding its framework in a classical deterministic view of the brain's physical processes, the document implicitly rejects the VNW and Orch theories we discussed. From the perspective of most physicists, this is a feature, not a bug. They would see the connection between quantum mechanics and consciousness as highly speculative, lacking in evidence, and not necessary to explain the phenomena in question. So that's actually the most important part. It's almost not important that quantum consciousness is highly speculative and lacking in evidence. The whole point that I arrive at the end here is that it's not even necessary to arrive at a practical way to think about our experience. Like if quantum mechanics, or if quantum science did have some effect in this equation, it's not a practical effect or an effect that we can practically now utilize. It is completely speculative and faith-based as far as we are concerned right now. The document's reliance on thinkers like Sean Carroll, a proponent of the deterministic many worlds interpretation, further aligns it with a significant segment of the physics community. In summary, the StanRichson document is highly relevant because it presents a coherent, scientifically grounded, and mainstream alternative to the idea that quantum physics has a special role in consciousness. The vast majority of neuroscientists would see its framework as a plausible and powerful way to conceptualize the mind, and the vast majority of physicists would agree with its fundamental approach of seeking answers at the level of neuroscience, not quantum mechanics. Okay, so then I mentioned this bibliographic complement that I put in here. We don't actually link to this because I don't mention anything about quantum physics in the document per se, or in part one, the full actual version, but I do note this, so we can just read this. I wanted to reference Something Deeply Hidden here. In Something Deeply Hidden, physicist Sean Carroll presents a compelling case for what is arguably the most straightforward interpretation of quantum mechanics, the many-world interpretation. Its elegance lies in its parsimony, as it takes the core Schrödinger equation at face value without adding an ad hoc wave function collapse. Instead, it follows the math to its logical conclusion that every possible outcome of a quantum event is real, each occurring in a separate parallel branch of the universe. Contrary to popular notions of quantum randomness, the many worlds posits that the universe as a whole is fundamentally deterministic, evolving according to predictable law. This deterministic foundation extends to the brain itself, which MW treats as a purely physical system. There is no need for a special conscious observer to play a privileged role. The brain's interactions simply cause it to become entangled with its environment, participating seamlessly in the branching of reality. Ultimately, Carroll's work offers a startling yet coherent picture where our familiar classical world emerges from a deeper quantum foundation. It provides a rigorous modern justification for the materialist and physicalist and law-abiding worldview that serves as the baseline for our own exploration into meaning and experience. Okay, so then I ask, does the bibliographic complement discussing Carroll's Something Deeply Hidden, which I just read, effectively acknowledge this contrast with quantum consciousness? It says yes, it does effectively and directly acknowledge the contrast with quantum consciousness theories. It achieves this by highlighting two core tenets of Carroll's many worlds interpretation that stand in stark opposition to the foundational claims of quantum consciousness. It explicitly removes the special conscious observer, and it rejects indeterminism and wave function collapse. Yep, so this worldview is one where consciousness is understood to be an emergent property of the physical brain with no special power to influence the fundamental laws of physics. This stands in direct and explicit contrast to the speculative theories of quantum consciousness. So yeah, that's where this conversation ends. That's where we can end right here. And I just wanted to go through that because that's one of the stops that we're taking really early on in the document, and I'm going to be posting the video of me reading through this first section, Collective Knowledge of the World. I'm basically trying to hit all the topics that we touch upon here that are necessary to have a discussion about. The next one's got to be evolution in the physical brain. Pretty much evolution. I think we should just talk about evolution for one day. Maybe even find a video, watch a video about evolution. That might be fun. I feel like evolution's a topic that we should do Evolution Day every month, honestly. Evolution deserves its own day a month.